Hello folks, welcome to Spark Interview Questions. I am Muthukumar. The session has been planned collectively to have commonly asked interview questions related to the Spark technology and the general answer, and the expectation is already you are aware of this particular technology to some extent, and in general the common questions being asked, as well as I'll give introduction about the technology as well. So let's get this started. So the agenda for this particular session is the basic questions we are going to cover, and questions related to the Spark Core technologies. That's when I say Spark Core, that's going to be the base. And top of Spark Core, we have 4 important components which work. That is streaming, graphics, MLlib, and SQL. All these components have been created to satisfy a specific requirement. I'll give introduction about these technologies and get into the commonly asked interview questions. And the question is also framed such a way it covers the spectrum of the doubts as well as the features available within that specific technology. So let's take the first question and look into the answer, like how commonly this is covered. What is Apache Spark? And Spark, it's with Apache Foundation now. It's an open source, it's a cluster computing framework for real-time processing. So 3 main keywords over here. Apache Spark, it's an open source project. It's used for cluster computing and for in-memory processing. Along with real-time processing, it's going to support in-memory computing. So there are lots of projects which supports cluster computing. Along with that, Spark differentiates itself by doing the in-memory computing. It's a very active community, and out of the Hadoop ecosystem technologies, Apache Spark is very active. Multiple releases we got last year. It's a very active project among the Apache projects. Basically, it's a framework going to support in-memory computing and cluster computing. And you may face this specific question, how Spark is different than MapReduce, or how you can compare it with the MapReduce. MapReduce is the processing methodology within the Hadoop ecosystem. And within Hadoop ecosystem, we have HDFS, Hadoop Distributed File System. MapReduce is going to support distributed computing. And how Spark is different. So how we can compare Spark with the MapReduce. In a way, this comparison going to help us to understand the technology better, but definitely like we cannot compare these two or 2 different methodologies by which it's going to work. Spark is very simple to program, but MapReduce, there is no abstraction, or the sense like all the implementations we have to provide. And interactivity, it has an interactive mode to work with in Spark. In MapReduce, there is no interactive mode. There are some components like Apache Pig and Hive, which facilitates us to do the interactive computing or interactive programming. And Spark supports real-time stream processing. And to precisely say, within Spark, the stream processing is called near real-time processing. There's nothing in the world is real-time processing. It's near real-time processing. It's going to do the processing in micro batches. I'll cover in detail when we are moving on to the streaming concept. I'm going to do the batch processing on the historical data in MapReduce. When I say stream processing, I'll get the data that is getting processed in real time and do the processing and get the result, either store it or publish it to public community. We will be doing it. Latency wise, MapReduce will have very high latency because it has to read the data from hard disk. But Spark, it will have very low latency because it can reprocess or use the data already cached in memory. But there's a small catch over here. In Spark, first time when the data gets loaded, it has to read it from the hard disk, same as MapReduce. So once it is read, it will be there in the memory. So Spark is good whenever we need to do iterative computing. So Spark, whenever you do iterative computing, again and again do the processing on the same data, especially in machine learning, deep learning, all we will be using the iterative computing. Here Spark's performance much better. You will see the Spark performance improvement 100 times faster than MapReduce. But if it is one-time processing and fire and forget, that type of processing, Spark, relatively it may be the same latency you will be getting it than MapReduce, maybe like some improvements because of the building block of Spark, that's the RDD. We may get some additional advantage. So that's the key feature or the key comparison factor of Spark and MapReduce. Now let's get on to the key features. Explain key features of Spark. We discussed about the speed and performance. It's going to use the in-memory computing. So speed and performance wise, it's going to much better when we do iterative computing. And it's a polyglot. In the sense, the programming language to be used with the Spark, it can be any of these languages. It can be Python, Java, R, or Scala. We can do programming with any of these languages. And data formats to give us an input, we can give any data formats like JSON, Parquet, any data formats we can give that as an input. And the key selling point with Spark is its lazy evaluation. In the sense, it's going to calculate the DAG cycle, directed acyclic graph, DAG, we call that as a DAG. It's going to calculate what all steps needs to be executed to achieve the final result. So we need to give all the steps as well as what final result I want. It's going to calculate the optimal cycle or optimal calculation, what all steps needs to be calculated or what all steps needs to be executed. Only those steps it will be executing it. So basically it's a lazy execution. Only if the results needs to be processed, it will be processing that specific result. And it supports real-time computing. It's through Spark Streaming. There is a component called Spark Streaming which supports real-time computing. And it gels with Hadoop ecosystem very well. It can run on top of Hadoop Yarn, or it can leverage the HDFS to do the processing. So when it leverages the HDFS, the Hadoop cluster container can be used to do the distributed computing, as well as it can leverage the resource manager to manage the resources. So Spark can gel with the HDFS very well, as well as it can leverage the resource manager to share the resources, as well as data locality it can leverage. Data locality, it can do the processing near to the data where data is located within the HDFS. And it has a fleet of machine learning algorithms already implemented, right from clustering, classification, regression, all those logic already implemented. And machine learning, it's achieved using MLlib within Spark. And there is a component called GraphX, which supports graph theory. So we can solve the problems using graph theory, using the component GraphX within the Spark. So these are the things we can consider as the key features of Spark. So when you discuss with the installation of the Spark, you may come across this Yarn. What is Yarn? Do you need to install Spark on all nodes of Yarn cluster? So Yarn is nothing but yet another resource negotiator. That's the resource manager within the Hadoop ecosystem. So that's going to provide the resource management platform. Yarn going to provide the resource management platform across all the clusters. And Spark, it's going to provide the data processing. So wherever the resource being used, that location, the Spark will be used to do the data processing. And of course, yes, we need to have Spark installed on all the nodes where Spark clusters are located. That's basically we need those libraries. And additional to the installation of Spark in all the worker nodes, we need to increase the RAM capacity on the worker machines as well. The Spark going to consume huge amount of memory to do the processing. It will not do the MapReduce way of working. Internally, it's going to generate the DAG cycle and do the processing on top of Yarn. So Yarn at the high level, it's like resource manager or like an operating system for the distributed computing. It's going to coordinate all the resource management across the fleet of servers. On top of it, I can have multiple components like Spark, Thais, Giraffe. So Spark, especially, it's going to help us to achieve in-memory computing. So Spark Yarn is nothing but it's a resource manager to manage the resource across the cluster. On top of it, we can have Spark. And yes, we need to have Spark installed in all the nodes of where the Spark Yarn cluster is used. And also additional to that, we need to have the memory increased in all the worker nodes. So next question was like this: what file system does Spark support? When I say file system, when we work in an individual system, we will be having a file system to work within that particular operating system. But in a distributed cluster or in a distributed architecture, we need a file system where we can store the data in a distributed mechanism. Hadoop comes with a file system called HDFS. It's called Hadoop Distributed File System, where data gets distributed across multiple systems, and it will be coordinated by two different types of components called name node and data node. And Spark, it can use this HDFS directly. So you can have any files in HDFS and start using it within the Spark ecosystem. And it gives another advantage of data locality. When it does the distributed processing, wherever the data is distributed, the processing could be done locally to that particular machine where data is located. And to start with, as a standalone mode, you can use the local file system as well. So this could be used especially when we are doing the development or any POC, we can use the local file system. And Amazon Cloud provides another file system called S3, Simple Storage Service. We call that as the S3. It's a block storage service. This can also be leveraged or used within Spark for the storage. And lot other file system also it supports. There are some file systems like Alexo, which provides in-memory storage. So we can leverage that particular file system as well. So we have seen all features, what all functionalities available within Spark. We're going to look at the limitations of using Spark. Of course, every component, when it comes with a huge power and advantage, it will have its own limitations as well. The next question illustrates some limitations of using Spark. Spark utilizes more storage space compared to Hadoop. When it comes to the installation, it's going to consume more space. But in the big data world, that's not a very huge constraint because storage cost is not very great or very high in big data space. A developer needs to be careful while running the apps in Spark. The reason because it uses in-memory computing. Of course, it handles the memory very well, but if you try to load a huge amount of data in the distributed environment, and if you try to do join, when you try to do join in the distributed world, the data are going to get transferred over the network. Network is really a costly resource. So the plan or design should be such a way to reduce or minimize the data transfer over the network. And however the way possible, with all possible means, we should facilitate distribution of the data over multiple machines. The more we distribute, the more parallelism we can achieve and the more results we can get. And cost efficiency, if you try to compare the cost, how much cost involved to do a particular processing, take any unit in terms of processing 1 GB of data with say like 5 iterative processing. If you compare cost wise, in-memory computing always it's costlier because memory it's relatively costlier than the storage. So that may act like a bottleneck and we cannot increase the memory capacity of the machine beyond some limit. So we have to grow horizontally. So when we have the data distributed in memory across the cluster, of course the network transfer, all those bottlenecks will come into picture. So we have to strike the right balance, which will help us to achieve the in-memory computing. Whatever the in-memory computing required, it will help us to achieve. And it consumes huge amount of data processing compared to Hadoop. And Spark, it performs better when user does iterative computing. Because like for both Spark and the other technologies, it has to read data for the first time from the hard disk or from other data source. And Spark performance is really better when it reads the data or does the processing when the data is available in the cache. Of course, yes, the DAG cycle, it's going to give us a lot of advantage while doing the processing. But the in-memory computing processing, that's going to give us lots of leverage. The next question lists some use cases where Spark outperforms Hadoop in processing. The first thing is the real-time processing. Hadoop cannot handle real-time processing, but Spark can handle real-time processing. So any data that's coming in the Lambda architecture, you will have 3 layers. And most of the big data projects will be in the Lambda architecture. You will have a speed layer, batch layer, and service layer. And the speed layer, whenever the data comes in, that needs to be processed, stored, and handled. So in those type of real-time processing, Spark is the best fit. Of course, within Hadoop ecosystem, we have other components which does the real-time processing like Storm. But when you want to leverage the machine learning along with the Spark streaming, all such computation, Spark will be much better. So that's why like when you have architecture like a Lambda architecture, you want to have all 3 layers, batch layer, speed layer, and service layer. Spark can gel the speed layer and service layer far better, and it's going to provide a better performance. And whenever you do the batch processing, especially like doing a machine learning processing, we will leverage the iterative computing and can perform 100 times faster than Hadoop. The more the iterative processing that we do, the more data will be read from the memory, and it's going to get us a much faster performance than Hadoop MapReduce. So again, remember, whenever you do the processing only once, so you're going to do the processing only once, read, process it, and deliver the result. Spark may not be the best fit. That can be done with the MapReduce itself. And there is another component called Akka. It's a messaging system or message coordinating system. Spark internally uses Akka for scheduling or any task that needs to be assigned by the master to the worker and a follow-up of that particular task by the master. Basically, asynchronous coordination system, and that's achieved using Akka. Akka programming internally it's used by the Spark. As such, for the developers, we don't need to worry about Akka programming. Of course, we can leverage it, but Akka is used internally by the Spark for scheduling and coordination between master and the worker. And within Spark, we have a few major components. Let's see what are the major components of Apache Spark. They name the components of Spark ecosystem. Spark comes with a core engine. So that has the core functionalities of what is required by the Spark or for the Spark. RDDs are the building blocks of the Spark core engine. On top of Spark core, the basic functionalities of file interaction, file system, coordination, all that's done by the Spark core engine. On top of Spark core engine, we have a number of other offerings to do machine learning, to do graph computing, to do streaming. We have a number of other components. So the majorly used components are these components like Spark SQL, Spark Streaming, MLlib, Graphics, and Spark R. At the high level, we will see what are these components. Spark SQL, especially, it's designed to do the processing against a structured data. So we can write SQL queries and we can handle or we can do the processing. So it's going to give us the interface to interact with the data, especially structured data, and the language that we can use. It's more similar to what we use within the SQL. I can say 99% it's same. And most of the commonly used functionalities within the SQL have been implemented within Spark SQL. And Spark Streaming is going to support the stream processing. That's the offering available to handle the stream processing. And MLlib is the offering to handle machine learning. So the component name is called MLlib and it has a list of components, a list of machine learning algorithms already defined. We can leverage and use any of those machine learning algorithms. Graphics, again, it's a graph processing offerings within the Spark. It's going to support us to achieve graph computing against the data that we have, like page rank calculation, how many connected entities, how many triangles, all those going to provide us a meaning to that particular data. And Spark R is the component that's going to interact or help us to leverage the language R within the Spark environment. R is a statistical programming language where we can do statistical computing within the Spark environment, and we can leverage R language by using the Spark R to get that executed within the Spark environment. Additional to that, there are other components as well, like approximate database, it's called BlinkDB, all other things like in beta stage. So these are the majorly used components within Spark. So next question, how can Spark be used alongside Hadoop? So when we say Spark performance much better, it's not a replacement to Hadoop. It's going to coexist with the Hadoop. So it's leveraging the Spark and Hadoop together. It's going to help us to achieve the best result. Yes, Spark can do in-memory computing or can handle the speed layer. And Hadoop comes with the resource manager. So we can leverage the resource manager of Hadoop to make Spark to work. And few processing, we don't need to leverage the in-memory computing. For example, one-time processing, do the processing and forget or just store it. We can use MapReduce. So the processing cost or computing cost will be much less compared to Spark. So we can amalgamize and strike the right balance between the batch processing and stream processing when we have Spark along with Hadoop. So let's have some detailed question related to Spark Core. Within Spark Core, as I mentioned earlier, the core building block of Spark Core is RDD, Resilient Distributed Dataset. It's a virtual, it's not a physical entity, it's a logical entity. You will not see this RDDs existing. The existence of RDD will come into picture when you take some action. So this RDD will be used or referred to create the DAG cycle, and RDDs will be optimized to transform from one form to another form, to make a plan how the data set needs to be transformed from one structure to another structure. And finally, when you take some against an RDD, the existence of the data structure, the resultant data will come into picture, and that can be stored in any file system, either HDFS, S3, or any other file system can be stored. And RDDs can exist in a partitioned form, in the sense it can get distributed across multiple systems. And it's fault tolerant. When I say fault tolerant, if any of the RDD is lost, any partition of the RDD is lost, it can regenerate only that specific partition it can regenerate. So that's the huge advantage of RDD. So if someone asks like what's the huge advantage of RDD, it's a fault tolerant where it can regenerate the last RDDs and it can exist in a distributed fashion and it is immutable. So since once the RDD is defined or like created, it cannot be changed. The next question is how do we create RDDs in Spark? There are two ways we can create the RDDs. One is using the Spark context. We can use any of the collections that's available within the Scala or in the Java, and using the parallelize function, we can create the RDD. And it's going to use the underlying file systems distribution mechanism. If the data is located in a distributed file system like HDFS, it will leverage that and it will make those RDDs available in a number of systems. So it's going to leverage and follow the same distribution in RDD as well. Or we can create the RDD by loading the data from external sources as well, like HBase. Generally, HDFS we may not consider as an external source. It will be considered as a file system of Hadoop. So when Spark is working with Hadoop, mostly the file system we will be using will be the HDFS. So we can read from HBase, or even we can read from other sources like Parquet file or from S3, different sources, Avro, we can read and create the RDD. Okay. Next question is, what is executor memory in Spark application? So every Spark application will have a fixed heap size and fixed number of cores for the Spark executor. Executor is nothing but the execution unit available in every machine, and that's going to facilitate to do the processing, to do the task in the worker machine. So irrespective of whether you use Yarn, Resource Manager, or any other Mesos like Resource Manager, every worker machine we will have one executor, and within the executor the task will be handled. And the memory to be allocated for that particular executor is what we define as the heap size, and we can define how much amount of memory should be used for that particular executor within the worker machine, as well as number of cores can be used within the executor or by the executor within the Spark application, and that can be controlled through the configuration files of Spark. Next question is, define partitions in Apache Spark. So any data, irrespective of whether it is small data or larger data, we can divide those data sets across multiple systems. The process of dividing the data into multiple pieces and making it to store across multiple systems as a different logical units is called partitioning. So in simple terms, partitioning is nothing but the process of dividing the data and storing in multiple systems is called partitions. And by default, the conversion of the data into RDD will happen in the system where the partition is existing. So the more the partition, the more parallelism we are going to get. At the same time, we have to be careful not to trigger huge amount of network data transfer as well. And every RDD can be partitioned within Spark. And the partitioning going to help us to achieve parallelism. More the partition that we have, more distributions can be done. And the key thing about the success of the Spark program is minimizing the network traffic while doing the parallel processing and minimizing the data transfer within the systems of Spark. What operations does RDD support? So I can operate multiple operations against the RDD. So there are two types of things we can do. We can group it into two. One is transformations. In transformations, RDD will get transformed from one form to another form. Say like filtering, grouping, all that is like it's going to get transformed from one form to another form. One small example like reduce by key, filter, all that will be transformations. The resultant of the transformation will be another RDD. At the same time, we can take some actions against the RDD that's going to give us the final result. I can say count how many records are there, or store that result into the HDFS. They all are actions. So multiple actions can be taken against the RDD. So the existence of the data will come into picture only if I take some action against the RDD. Okay, next question. What do you understand by transformations in Spark? So transformations are nothing but functions. Mostly it will be higher order functions. Within Scala, we have something like a higher order functions, which will be applied against that RDD. Mostly against the list of elements that we have within the RDD, that function will get applied. But the existence of the RDD will come into picture only if we take some action against it. In this particular example, I am reading the file and having it within the RDD called raw data. Then I am doing some transformation using a map. So it's going to apply a function. So within map, I have some function which will split each record using the tab. So the split with the tab will be applied against each record within the raw data. And the resultant movies data will again be another RDD. But of course, this will be a lazy operation. The existence of movies data will come into picture only if I take some action against it, like count or print or store. Only those actions will generate the data. So next question, define functions of Spark Core. So that's going to take care of the memory management and fault tolerance of RDDs. It's going to help us to schedule, distribute the task, and manage the jobs running within the cluster. And so going to help us to store the data in the storage system as well as read the data from the storage system. That's to do the file system level operations. It's going to help us. And Spark Core programming can be done in any of these languages like Java, Scala, Python, as well as using R. So core is at the horizontal level. On top of Spark Core, we can have a number of components. And there are different type of RDDs available. One such special type is pair RDD. So next question, what do you understand by pair RDD? So it's going to exist in pairs as a keys and values. So I can do some special functions within the pair RDDs or special transformations, like collect all the values corresponding to the same key, like sort and shuffle. What happens within the sort and shuffle of Hadoop? Those type of operations, like you want to consolidate or group all the values corresponding to the same key, or apply some functions against all the values corresponding to the same key. Like I want to get the sum of the value of all the keys. We can use the pair RDD and get that achieved. So it's going to, the data within the RDD going to exist in pairs, keys and values. All right. Okay. Question from Jason. What are vector RDDs? In machine learning, you will have a huge amount of processing handled by vectors and matrices. And we do lots of operations, vector operations like effective vector or transforming any data into a vector form. So vectors, like as the normal way, it will have a direction and magnitude. So we can do some operations like sum two vectors, and what is the difference between the vector A and B as well as A and C. If the difference between vector A and B is less compared to A and C, we can say the vector A and B is somewhat similar, okay, in terms of features. So the vector RDD will be used to represent the vector directly, and that will be used extensively while doing the machine learning. Yeah, Jason, thank you. And there's another question, what is RDD lineage? So here, any data processing, any transformations that we do, it maintains something called a lineage. So how data is getting transformed? When the data is available in a partitioned form in multiple systems, and when we do the transformation, it will undergo multiple steps. And in the distributed world, it's very common to have failures of machines or machines going out of the network. And the system or framework, as such, it should be in a position to handle. Spark handles it through RDD lineage. So it can restore the last partition only. Assume like out of 10 machines, data is distributed across 5 machines. Out of that, those 5 machines, 1 machine is lost. So whatever the latest transformation that had that data for that particular partition, the partition in the last machine alone can be regenerated. And it knows how to regenerate that data or how to get that resultant data using the concept of RDD lineage. So from which data source it got generated, what was its prior step, so the complete lineage will be available. And it's maintained by the Spark framework internally. We call that as RDD lineage. What is Spark driver? To put it simply for those who are from Hadoop background, Yarn background, we can compare this to AppMaster. Every application will have a Spark driver that will have a Spark context which is going to coordinate the complete execution of the job. That will connect to the Spark master and delivers the RDD graph, that is the lineage, to the master, and coordinate the tasks, whatever the task that gets executed in the distributed environment. It can do the parallel processing, do the transformations and actions against the RDD. So it's a single point of contact for that specific application. So Spark driver is a short-lived, and the Spark context within the Spark driver is going to be the coordinator between the master and the tasks that are running. And Spark driver can get started in any of the executor within Spark. Okay. Name types of cluster managers in Spark. So whenever you have a group of machines, you need a manager to manage the resources. There are different type of cluster manager. Already we have seen the Yarn, yet another resource negotiator, which manages the resources of Hadoop. On top of Yarn, we can make Spark to work. Sometimes I may want to have Spark alone in my organization and not along with the Hadoop or any other technology. Then I can go with the standalone. Spark has built-in cluster manager. So only Spark can get executed in multiple systems. But generally, if we have a cluster, we will try to leverage various other computing platforms or computing frameworks like graph processing, Giraffe, These, all that we will try to leverage. In that case, we will go with Yarn or some generalized resource manager like Mesos. Yarn is very specific to Hadoop and it comes along with Hadoop. Mesos is a cluster level resource manager. When I have multiple clusters within an organization, then I can use Mesos. Mesos is also a resource manager. It's a separate top level project within Apache. Next question, what do you understand by worker node? So in a cluster, in a distributed environment, we will have n number of workers. We call that as a worker node or a slave node, which does the actual processing. Going to get the data, do the processing and get us the result. And master node going to assign what task to be done by what worker node. And it's going to read the data available in that specific worker node. Generally, the task assigned to the worker node or the task will be assigned to the worker node where data is located. In big data space, especially Hadoop, always it will try to achieve the data locality. That's what we call it the resource availability, as well as the availability of the resource in terms of CPU, memory as well will be considered. Assume I have some data replicated in 3 machines. All 3 machines are busy doing the work and no CPU or memory available to start the other task. It will not wait for those machines to complete the job and get the resource and do the processing. It will start the processing in some other machine which is going to be near to that, the machines having the data, and read the data over the network. So to answer straight, worker machines are nothing but which does the actual work and going to report to the master in terms of what is the resource utilization, and the tasks running within the worker machines will be doing the actual work. And what is a sparse vector? Just few minutes back I was answering a question like what is a vector? Vector is nothing but representing the data in multidimensional form. A vector can be multidimensional vector as well. Assume I am going to represent a point in space. I need 3 dimensions, x, y, and z. So the vector will have 3 dimensions. If I need to represent a line in the space, then I need 2 points to represent the starting point of the line and the end point of the line. Then I need a vector which can hold, so it will have 2 dimensions. The first dimension will have 1 point, the second dimension will have another point. At the same way, if I have to represent a plane, then I need another dimension to represent 2 lines. So each line will be representing 2 points. Same way I can represent any data using a vector form. Assume I have huge number of feedback or ratings of products across an organization. Let's take a simple example, Amazon. Amazon have millions of products. Not every user, not even a single user would have used millions of all the products within Amazon. So only hardly we would have used like a 0.1% or like even less than that. Maybe like few hundred products we would have used and rated the products within Amazon for the complete lifetime. If I have to represent all ratings of the products with a vector, I'll say the first position of the rating, it's going to refer to the product with ID 1. Second position, it's going to refer to the product with ID 2. So I'll have million values within that particular vector. Out of million values, I'll have only values for 100 products where I have provided the ratings. So it may vary from number 1 to 5. For all others, it will say 0. Sparse means thinly distributed. Yeah. So to represent the huge amount of data with the position saying this particular position is having a 0 value, we can mention that with a key and value. So what position having what value? Rather than storing all zeros, I can store only non-zeros, the position of it and the corresponding value. That means all others going to be a 0 value. So we can mention this particular sparse vector, mentioning it to represent the non-zero entities. So to store only the non-zero entities, the sparse vector will be used, so that we don't need to waste additional space while storing the sparse vector. Let's discuss some questions on Spark streaming. How is streaming implemented in Spark? Explain with examples. Spark streaming is used for processing real-time streaming data to precisely say it's a micro batch processing. So data will be collected between every small interval, say maybe like 0.5 seconds or every seconds, and it will get processed. So internally it's going to create micro batches. The data created out of that micro batch we call that is a D stream. D stream is like a RDD. So I can do transformations and actions, whatever that I do with RDD, I can do it with D stream as well. And Spark streaming can read data from Flume, HDFS, or other streaming sources as well, and store the data in the dashboard or in any other database. And it provides a very high throughput as it can be processed with a number of different systems in a distributed fashion. Again, DStream will be partitioned internally, and it has the built-in feature of fault tolerance. Even if any data is lost, any transformed RDD is lost, it can regenerate those RDDs from the existing or from the source data. So DStream is going to be the building block of streaming, and it has the fault tolerance mechanism what we have within the RDD. So DStream or specialized RDD, specialized form of RDD, specifically to use it within the Spark streaming. Okay, next question, what is the significance of sliding window operation? That's a very interesting one. In the streaming data, whenever we do the computing, the data density or the business implications of that specific data may oscillate a lot. For example, within Twitter, we used to say the trending tweet hashtag. Just because that hashtag is very popular, maybe someone might have hacked into the system and used a number of tweets. Maybe for that particular hour, it might have appeared millions of times. Just because it appeared millions of times for that specific a minute duration, or like say 2-3 minute duration, it should not get into the trending tag or trending hashtag for that particular day or for that particular month. So what we will do, we will try to do an average. So like a window, this current time frame and t-1, t-2, all the data we will consider, and we will try to find the average or sum. So the complete business logic will be applied against that particular window. So any drastic changes, or to precisely say the spike or dip, any drastic spike or drastic dip in the pattern of the data will be normalized. So that's the biggest significance of using the sliding window operation within Spark streaming. And Spark can handle this sliding window automatically. It can store the prior data, the t-1, t-2, and how big the window needs to be maintained. All that can be handled easily within the program, handles at the abstract level. Next question is, what is DStream? The expansion is discretized stream. So that's the abstract form or the visual form of representation of the data for the Spark streaming. The same way how RDD getting transformed from one form to another form, we will have series of RDDs all put together called as a DStream. So DStream is nothing but it's another representation of RDD, or like a group of RDDs. We call that as a DStream, and I can apply the streaming functions or any of the functions, transformations or actions available within the streaming against this DStream. So within that particular micro batch, so I'll define what interval the data should be collected or should be processed. We call that as a micro batch. It could be every 1 second or every 100 milliseconds or every 5 seconds. I can define that particular period. So all the data received in that particular duration will be considered as a piece of data, and that will be called as a DStream. Next question, explain caching in Spark streaming. Of course, yes, Spark internally it uses in-memory computing. So any data when it is doing the computing that's getting generated, it will be there in memory. But further, if you do more and more processing with the other jobs, when there is a need for more memory, the least used RDDs will be cleared off from the memory, or the least used data available out of actions from the RDD will be cleared off from the memory. Sometimes I may need that data forever in memory. Very simple example like dictionary. I want the dictionary words should be always available in memory because I may do a spell check against the tweet commands or feedback commands a number of times. So what I can do, I can say cache those, any data that comes in, we can cache it or persist it in memory. So even when there is a need for memory by other applications, this specific data will not be removed. And especially that will be used to do the further processing. And the caching also can be defined, whether it should be in memory only or in memory and hard disk, that also we can define it. Let's discuss some questions on Spark graphics. So next question is there an API for implementing graphs in Spark? So in graph theory, everything will be represented as a graph. When I say graph, it will have nodes and edges. So all will be represented using the RDDs. So it's going to extend the RDD, and there is a component called graphics, and it exposes the functionalities to represent a graph. We can have a edge RDD, vertex RDD. By creating the edges and vertex, I can create a graph, and this graph can exist in a distributed environment. So same way we will be in a position to do the parallel processing as well. So graphics is just a form of representing the data, the graphs with edges and vertices. And of course, yes, it provides the API to implement or create the graph, do the processing on the graph. The APIs are provided. What is PageRank in graphics? So within graphics, once the graph is created, we can calculate the PageRank for a particular node. So that's very similar to how we have the PageRank for the websites within Google. The higher the PageRank, that means it's more important within that particular graph. It's going to show the importance of that particular node or edge within that particular graph. When I say graph, it's a connected set of data. All data will be connected using the property, and how much important that property makes. We will have a value associated to it. So within PageRank, we can calculate like a static PageRank. It will run a number of iterations. Or there is another PageRank or dynamic PageRank that will get executed till we reach a particular saturation level. And the saturation level can be defined with multiple criteria. And the APIs, we call that as a graph operations, can be directly executed against those graph, and they all are available as API within the graphics. What is lineage graph? So the RDD is very similar to the graphics, how the graph representation. Every RDD internally, it will have the relation saying how that particular RDD got created and from where, how that got transformed. RDD is how they got transformed. So the complete lineage or the complete history or the complete path will be recorded within the lineage. That will be used in case if any particular partition of that RDD is lost, it can be regenerated. Even if the complete RDD is lost, we can regenerate. So it will have the complete information on what all partitions, where it is existing, what all transformations it had undergone, what is the resultant value. If anything is lost in the middle, it knows where to recalculate from and what all essential things needs to be recalculated. It's going to save us a lot of time. And if that RDD is never being used, it will never get recalculated. So the recalculation also triggers based on the action. Only on need basis it will recalculate. That's why it's going to use the memory optimally. Does Apache Spark provide checkpointing? Especially like take the example like streaming. And if any data is lost within that particular sliding window, we cannot get back the data, or like the data will be lost. Assume I'm making a window of say 24 hours. To do some average, I'm making a sliding window of 24 hours. Every 24 hours it will keep on getting slided. And if you lose any system, assume there is a complete failure of the cluster, I may lose the data because it's all available in the memory. So how to recalculate if the data system is lost? It follows something called a checkpointing. So we can checkpoint the data, and directly it's provided by the Spark API. We have to just provide the location where it should get checkpointed. And you can read that particular data back when you start the system again. Whatever the state it was in, we can regenerate that particular data. So yes, to answer the question straight, Apache Spark provides checkpointing, and it will help us to regenerate the state what it was earlier. Let's move on to the next component, Spark MLlib. How is machine learning implemented in Spark? So machine learning, again, it's a very huge ocean by itself, and it's not a technology specific to Spark. Machine learning is a common data science. It's a subset of data science world, where we have different type of algorithms, different categories of algorithm like clustering, regression, dimensionality reduction, all that we have. And all these algorithms, or most of the algorithms, have been implemented in Spark. And Spark is the preferred framework or preferred application component to do the machine learning algorithm nowadays, or machine learning processing. The reason because most of the machine learning algorithms needs to be executed iteratively a number of times till we get the optimal result. Maybe like say 25 iterations or 50 iterations, or till we get that specific accuracy. We will keep on running the processing again and again. And Spark is very good fit whenever you want to do the processing again and again, because the data will be available in memory. I can read it faster, store the data back into the memory, again read it faster. And all these machine learning algorithms have been provided within the Spark as a separate component called MLlib. And within MLlib, we have other components like featureization to extract the features. You may be wondering how we can process the images. The core thing about processing an image or audio or video is about extracting the feature and comparing the feature, how much they are related. So that's where vectors, matrices, all that will come into picture. And we can have pipeline of processing as well. Do the processing 1, then take the result and do the processing 2. And it has persistence algorithm as well. The result of it, the generated or processed result, it can be persisted and reloaded back into the system to continue the processing from that particular point onwards. Next question, what are categories of machine learning? Machine learning as such, different categories available: supervised, unsupervised, and reinforced learning. Supervised, unsupervised, it's very popular, where we will know, I'll give with an example. I'll know well in advance what category that belongs to. Assume I want to do a character recognition. While training the data, I can give the information saying this particular image belongs to this particular category, character, or this particular number, and I can train. Sometimes I'll not know well in advance. Assume like I may have different type of images, like it may have cars, bikes, cat, dog, all that. I want to know how many category available. I'll not know well in advance. So I want to group it, how many category available. And then I'll realize saying, okay, all this belongs to a particular category. I'll identify the pattern within that category and I'll give a category name. Say like all these images belongs to boat category. All looks like a boat. So leaving it to the system by providing this value or not. That's where the different type of machine learning comes into picture. And as such, machine learning is not specific to Spark. It's going to help us to achieve to run these machine learning algorithms. What are Spark MLlib tools? MLlib is nothing but machine learning library or machine learning offering within the Spark. It has a number of algorithms implemented, and it provides a very good feature to persist the result. Generally in machine learning, we will generate a model. The pattern of the data, we call that as a model. The model will be persisted either in different forms like Parquet, Avro, different forms it can be stored or persisted, and has methodologies to extract the features from a set of data. I may have a million images. I want to extract the common features available within those millions of images, and there are other utilities available to process, to define, or like to define the seed, the randomizing it. So different utilities available, as well as pipelines. That's very specific to Spark, where I can channel or arrange the sequence of steps to be undergone by the machine learning. So machine learning 1 algorithm first, and then the result of it will be fed into machine learning algorithm 2. Like that, we can have a sequence of execution, and that will be defined using the pipelines. These all are inbuilt features of Spark MLlib. What are some popular algorithms and utilities in Spark MLlib? So these are some popular algorithms like regression, classification, basic statistics, recommendation systems. Recommendation system is like well implemented. All we have to provide is give the data. If you give the ratings and products within an organization, if you have the complete dump, we can build the recommendation system in no time. And if you give any user, it can give a recommendation. These are the products the user may like, and those products can be displayed in the search result. Recommendation system purely works on the basis of the feedback that we are providing for the earlier products that we had bought. Clustering, dimensionality reduction. Whenever we do processing with a huge amount of data, it's very, very compute intensive, and we may have to reduce the dimensions, especially the matrix dimensions within the MLlib, without losing the features. Whatever the features available, without losing it, we should reduce the dimensionality. And there are some algorithms available to do that dimensionality reduction. And feature extraction. So what are all the common features or features available within that particular image? And I can compare what are all the common features available within those images. That's why we will group those images. So get me whether this particular image, the person looking like this image available in the database or not. For example, assume the organization or the police department, crime department maintaining a list of persons committed crime. And if they get a new photo, when they do a search, they may not have the exact photo bit by bit. The photo might have been taken with a different background, different lightings, different locations, different time. So 100% the data will be different, or bits and bytes will be different. but look-wise, yes, they are going to be same. So I'm going to search the photo looking similar to this particular photograph as the input I'll provide. To achieve that, we will be extracting the features. In each of those photos, we will extract the features and we will try to match the feature rather than the bits and bytes. And optimization as well in terms of processing or doing the piping. There are a number of algorithms to do the optimization. Let's move on to Spark SQL. Is there a module to implement SQL in Spark? How does it work? So directly not the SQL, maybe very similar to Hive. Whatever the structured data that we have, we can read the data or extract the meaning out of the data using SQL. And it exposes the API, and we can use those API to read the data or create data frames. And Spark SQL has 4 major categories: data source, data frame. Data frame is like the representation of X and Y data, or like a Excel data, multidimensional structure data in abstract form. On top of data frame, I can do the query. And internally, it has the interpreter and optimizer. Any query I fire, that will get interpreted or optimized and will get executed using the SQL services and get the data from the data frame, or it can read the data from the data source and do the processing. What is a Parquet file? It's a format of the file where the data in some structured form, especially the result of the Spark SQL, can be stored or returned in some persistence. And the Parquet, again, it is open source from Apache. It's a data serialization technique where we can serialize the data using the Parquet form. And to precisely say, it's a columnar storage. It's going to consume less space. It will use the keys and values and store the data. And also it helps you to access a specific data from that Parquet form using the query. So Parquet, it's another open source format, data serialization form, to store the data or persist the data as well as to retrieve the data. List the functions of Spark SQL. It can be used to load the varieties of structured data. Of course, yes, Spark SQL can work only with the structured data. It can be used to load varieties of structured data. And you can use SQL-like statements to query against the program. And it can be used with external tools to connect to the Spark as well. It gives a very good integration with the SQL. And using Python, Java, or Scala code, we can create a RDD from the structured data available. Directly using the Spark SQL, I can generate the RDD. So it's going to facilitate the people from database background to make the program faster and quicker. Next question is, what do you understand by lazy evaluation? So whenever you do any operation within the Spark world, it will not do the processing immediately. It will look for the final result that we are asking for it. If it doesn't ask for the final result, it doesn't need to do the processing. So based on the final action, till we do the action, there will not be any transformations, or there will not be any actual processing happening. It will just understand what are transformations it has to do. Finally, if you ask for the action, then in an optimized way, it's going to complete the data processing and get us the final result. So to answer straight, lazy evaluation is doing the processing only on need of the resultant data. If the data is not required, it's not going to do the processing. Can you use Spark to access and analyze data stored in Cassandra database? Yes, it is possible. Okay, not only Cassandra, any of the NoSQL database, it can very well do the processing. And the Cassandra also works in a distributed architecture. It's a NoSQL database. So it can leverage the data locality. The query can be executed locally where the Cassandra nodes are available. That's going to make the query execution faster and reduce the network load. And Spark executors, it will try to get started, or the Spark executors in the machine where the Cassandra nodes are available or data is available, it's going to do the processing locally. So it's going to leverage the data locality. Next question, how can you minimize data transfers when working with Spark? If you ask the core design, the success of the Spark program depends on how much you are reducing the network transfer. Because network transfer is very costly operation and you cannot parallelize. It gives multiple ways, or especially 2 ways to avoid this. One is called broadcast variable and accumulators. Broadcast variable, it will help us to transfer any static data or any informations, keep on publishing it to multiple systems. So I'll say if any data to be transferred to multiple executors to be used in common, I can broadcast it. Or I might want to consolidate the values happening in multiple workers in a single centralized location, I can use accumulator. So this will help us to achieve the data consolidation or data distribution in the distributed world at the API level or at the abstract level, where we don't need to do the heavy lifting. That's taken care by the Spark for us. What are broadcast variables? Just now, as we discussed, the value, the common value that we need, I may want that to be available in multiple executors, multiple workers. Simple example, you want to do a spell check on the tweet comments. The dictionary, which has the right list of words, I'll have the complete list. I want that particular dictionary to be available in each executor, so that with a task that's running locally in those executors can refer to that particular map task and get the processing done by avoiding the network data transfer. So the process of distributing the data from the Spark context to the executors where the task is going to run is achieved using broadcast variables. And it's built in within the Spark API. Using the Spark API, we can create the broadcast variable. And the process of distributing this data available in all executors is taken care by the Spark framework. Explain accumulators in Spark. The similar way how we have broadcast variables, we have accumulators as well. Simple example, you want to count how many error records are available in the distributed environment. Assume data is distributed across multiple systems, multiple executors. Each executor will do the processing, count the records, and atomically I may want the total count. So what I'll do, I'll ask to maintain an accumulator. Of course, it will be maintained in the Spark context in the driver program, because the driver program is going to be one per application. It will keep on getting accumulated, and whenever I want, I can read those values and take any appropriate action. So it's like more or less the accumulators and broadcast variables looks opposite to each other, but the purpose is totally different. Why is there a need for broadcast variable when working with Apache Spark? It's a read-only variable, and it will be cached in memory in a distributed fashion, and it eliminates the work of moving the data from a centralized location, that is a Spark driver or from a particular program, to all the executors within the cluster where the task is going to get executed. We don't need to worry about where the task will get executed within the cluster. So when compared with the accumulators, broadcast variables, it's going to have a read-only operation. The executors cannot change the value. It can only read those values. It cannot update. So mostly it will be used like a cache that we have for the RDD. Next question, how can you trigger automatic cleanups in Spark to handle accumulated metadata? So there is a parameter that we can set, TTL, that will get triggered along with the running jobs, and intermediately it's going to write the data result into the disk or clean the unnecessary data or clean the RDDs that's not being used. The least used RDD, it will get cleaned, and it will keep the metadata as well as the memory clean. What are the various levels of persistence in Apache Spark? When we say data should be stored in memory, it can be in different levels, it can be persisted. So it can be in memory only, or memory and disk, or disk only. And when it is getting stored, we can ask it to store it in a serialized form. So the reason why we may store or persist is, I want this particular RDD, this form of RDD later back for reusing. So I can read it back. Maybe I may not need it very immediately, so I don't want that to keep occupying my memory. I'll write it to the disk and I'll read it back whenever there is a need. I'll read it back. The next question, what do you understand by schema RDD? So schema RDD will be used especially within the Spark SQL. So the RDD will have the meta information built into it. It will have the schema also, very similar to what we have the database schema, the structure of that particular data. And when I have the structure, it will be easy for me to handle the data. So data and the structure will be existing together. And the schema RDD now it's called as a data frame within Spark. And data frame term is very popular in languages like R, SAS, other languages, it's very popular. So it's going to have the data and the meta information about that data, saying what column, what structure it is in. Explain the scenario where you will be using Spark streaming. Assume you want to do a sentiment analysis of tweeters. So data will be streamed. So we will use a Flume sort of a tool to harvest the information from Twitter and feed it into Spark streaming. It will extract or identify the sentiment of each and every tweet and mark it whether it is positive or negative. And accordingly, the data will be the structured data, the tweet ID, whether it is positive or negative, maybe percentage of positive and percentage of negative sentiment. Store it in some structured form. Then you can leverage the Spark SQL and do grouping or filtering based on the sentiment. And maybe I can use a machine learning algorithm. What drives that particular tweet to be in the negative side? Is there any similarity between all those negative tweets? Maybe specific to a product or specific time by when the tweet was tweeted, or from a specific region the tweet was tweeted. So those analysis could be done by leveraging the MLlib of Spark. So MLlib, streaming, core, all going to work together. All these are like different offerings available to solve different problems. So with this, we are coming to end of this interview questions discussion of Spark. I hope you all enjoyed. I hope it was a constructive and useful one. The more information about Edureka is available in this website, edureka.co. All the best, and keep visiting the website for blogs and latest updates. Thank you, folks.
I hope you enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply to them at the earliest. Do look out for more videos in our playlist and subscribe to our Edureka channel to learn more. Happy learning!